Hello everyone. Today I will be presenting project on Piecewise Linear Contrast Stretching. This is simple but powerful image processing technique that improves the clarity and the visual quality of the grayscale images, especially those that appear dull or underexposed. In this presentation, I will walk you through what the problem is, how the mathematical technique works, and the logic behind the code implementation, and how it visibly enhances the image's dynamic range and brightness. The goal is to show how even a basic mathematical transformation can make a major difference in how image looks and how useful it becomes for analysis. Low contrast images are very common when photos are captured in poor lighting or with low quality sensors. In such images, the intensity range of the pixel is squeezed into a small band rather than spread across the full scale of 0 to 255. This narrow range makes the picture appear flat, grey, and lacking depth. The details that should stand out are hidden in shadows or faded in highlights. For example, an underexposed grayscale image may have most of its pixel values between 60 and 150, which severely limits the contrast. Our objective is to stretch this limited range so the full brightness scale is better utilized, producing a more balanced and dynamic image that feels natural and visually appealing.
To solve this problem, we use a method called Piecewise Linear Contrast Stretching. The idea is straightforward. Instead of using one uniform contrast stretching adjustment for entire image, we divide the intensity range into smaller segments and apply different linear transformations to each. Imagine plotting input pixel values along the x-axis and output values along the y-axis. A single straight line mapping affects every region equally, but in a piecewise function, each section of the curve has its own slope and intercept. This lets us brighten darker areas more aggressively, keep midtones natural, and prevent bright regions from becoming overexposed. By treating each region independently, we gain fine-grained control over brightness and contrast, leading to far better visual results than traditional methods. The mathematical foundation behind this method is simple but effective. The transformation is expressed as a set of linear equations of the form S equal m times r plus c, where r represents the input intensity, s is the output intensity, m is the slope that controls contrast, and c is the constant that shifts the brightness. Multiple breakpoints such as R1, R2 and R3 are chosen to divide the image intensity range into sections. Each section uses its own slope value. A steep slope greater than 1 stretches the contrast in that region, while a shallow slope compresses it. By carefully choosing these slopes and breakpoints, we can expand the darker areas, fine-tune midtones, and preserve highlights. This mathematical flexibility allows the transformation to adapt to almost any kind of low contrast image.
The implementation of this concept was done in Python using the OpenCV library, which is widely used for image processing tasks. The grayscale image is first read using the imread function, converting it into a matrix of pixel values ranging from 0 to 255. The values are then normalized between 0 and 1 for easier computation. Next, we define the breakpoints and slope values for each segment of the piecewise function. Using these parameters, the program maps every pixel through the appropriate equation to generate the new intensity values. Finally, both the original and the enhanced images are displayed side by side using matplotlib. What's powerful about this approach is that it uses pure mathematics, no filters or deep learning models, yet it produces a dramatic improvement in visibility and tone. When we compare the results, the improvement is immediately noticeable. The original image appears dull and flat, with limited separation between dark and bright regions. After applying the piecewise linear contrast stretching, the enhanced image shows a richer tonal range. Dark areas reveal more detail, midtones appear clearer, and highlights remain controlled instead of washed out. If we look at the histogram, we can see how the pixel values have expanded. across a wider range, representing a significant boost in a dynamic range. This expansion not only increases contrast but also brings out the subtle texture that were hidden before. The same principle is used in many professional applications such as medical imaging to improve X-rays and MRI scans or satellite imaging to enhance terrain details. It's a simple yet very practical method.
In summary, piecewise linear contrast stretching is an effective and efficient way to enhance grayscale images. It divides the pixel intensity range into smaller regions and adjusts each one with a suitable linear mapping, resulting in balanced brightness and improved visibility. Compared to normal contrast stretching, it delivers the much better results for images with uneven exposure or lighting conditions. Through this presentation, we saw the theory, mathematical concept, code implementation, and final visual improvements. Thank you for watching and taking time to understand this image enhancement technique.